So here we do have a circuit that regulates voltage. This is the most basic voltage regulator circuit you can have. And if you look at this circuit, it's what we saw in the last video with the addition of a Zener diode connected in parallel with the load. Remember, this is the anode side of the Zener diode, and this is the cathode side. Okay, so in this example, VZ is 12 volts. Okay, and again, that was taken from the data sheet. VZ is just a spec that you look up. Alright, so let's see how, with the addition of this Zener diode, this circuit now does regulate voltage. So to do so, we have to find the state of the Zener diode within this range, this specified range of 50 to 250 ohms, which again represents how much current's being drawn from the car battery in our car example. So the 50 ohm again is when all the accessories are on, we're drawing the most current from the battery, and the 250 ohms is when all the accessories we have control over are off and we're drawing a minimum amount of current from the battery. So just like with non-Zener diodes, in order to find the state, we use the ideal diode model. Well, with a Zener diode, and we always will assume Zener diodes are ideal in this class, we're going to use the ideal Zener model that was mentioned a couple of videos ago. So if I back up a few pages, right here is our model. Now there was one typo that I made in the previous, well actually not a typo, it was an omission. There was one error I made in the first video, the original video where I talked about this model, and that's I forgot this equality sign here for this condition that when the voltage across the Zener VD is equal to or less than the VZ amount, again where that VZ amount is negative, the negative meaning reverse bias voltage, well then you have this condition of the Zener diode conducting. So I forgot to put in that equal sign, I just had the less than in the previous video. Alright, so just like you make an open assumption for non-Zener diodes to find the state using the ideal diode model, well with the ideal Zener model you'll also make an open assumption. Okay, reverse bias open. So you see I took the Zener diode symbol, replaced it with an open, and now the voltage across this open, okay, defined with the plus on anode, that's the diode voltage. So we need to find what this diode voltage is and then compare it to the model to see whether our assumption of reverse bias open was correct. Now one thing that's definitely true is that with the Zener diode connected in the circuit, as you see, there's no way the Zener diode could be forward bias, because see the anode's attached to ground, okay, which means VA is 0 volts, and remember diode voltage VD is equal to VA minus VK. So you see we're going to have 0 minus some positive number, because VK, that's the voltage at this node here, right, with respect to ground. And since the negative side of this voltage source is grounded, VK has got to be a positive number. So as long as the anode is grounded, as you see like this, the Zener diode is going to be reverse bias, okay, because VD here is going to come out to a negative number. But the question is it reverse bias acting like an open, okay, not conducting, or is it reverse bias acting like a voltage source of value VZ conducting? See, that's what the question is, and that's what VK, the value of VK, will determine. So to find VK, well, this is the same analysis as we did earlier. Since the Zener diode is being represented with an open, it's the same as what we did right here. Okay, that when RL is 50 ohms, okay, and that's the RL value we'll start with here. RL equal to 50 ohms. Well, VK is going to be 12. So VD is minus 12 volts. Okay, so now we go to the Zener model, the ideal Zener model, and again VZ 12 volts. When we put it into the model, we put a minus sign there. VD came out to minus 12 volts, so we're in this part of the model that our reverse bias open assumption was incorrect, that the Zener diode is actually reverse bias conducting, acting like a voltage source of VZ. See, when VD equals VZ, like we have in this case, right, because we got minus 12 on both sides here, that's the condition where we just have enough reverse bias volts to get the ripping of electrons to occur that we talked about in this video here, that we first discussed this model. And when the ripping of electrons occurs, that's when the Zener is conducting and it acts like an ideal voltage source of VZ. So really what we have is that the Zener diode is acting like this 12 volt voltage source. Okay, so you see for 50 ohms, when RL is 50 ohms, VRL, okay, VRL is the voltage across RL. Well, look, if the Zener is acting like a 12 volt voltage source, okay, and notice also that I put the plus side of this voltage source, oops, to the cathode side, like we talked about earlier. The anode's grounded. Okay, so this Zener is in parallel with the load, so if it's acting like a 12 volt source, that means you're going to have 12 volts across RL, okay, because voltages are the same in parallel, like you learned in your circuit theory. Alright, so now let's look at when RL is 150 ohms. Okay, so now this circuit with RL equal to 150 ohms, we're going to have VD equal to 0 minus, because again, VA is always going to be 0 since it's grounded. But now VK, the voltage from this node to ground, is the same as what we had across RL here without the Zener diode, right? Because when the Zener diode's in open, it is this circuit. So we have 18 volts for VK. Okay, so VD is minus 18 volts. So now we go to the ideal Zener model, and we're still in this bottom row here, that now VD is minus 18, so it's much less, or it's less than the VZ amount of minus 12 volts. So the Zener is still reverse bias and conducting, acting like a voltage source of VZ. So here we have plenty of reverse bias volts. We have 6 more reverse bias volts than what the minimum is in order to get the ripping of electrons and to cause the conduction through the Zener in the reverse bias direction and for it to act like an ideal voltage source of VZ. So when RL is 150 ohms, the Zener is still acting like a voltage source of VZ, so that maintains 12 volts across the load, right? Because as long as the Zener is acting like a voltage source, the load's going to have the same voltage since they're in parallel. And then just to finish this off, if you have RL equal to 200 ohms, or 250 ohms, excuse me, which is the top value of the range, well, you should be able to prove to yourself that now VD is going to be minus 20 volts, okay, which is even more reverse bias voltage than we need to get the Zener to conduct, right? It's 8 more reverse bias volts than what the minimum that we need. So throughout this entire range, the specified range of RL from 50 ohms to 250 ohms, the Zener maintains the same voltage, the VZ amount, 12 volts across the load, since it's conducting, acting like a voltage source of 12 volts. Okay, and this is voltage regulation because here RL is changing through a specified range and the load voltage is maintained constant. And this is very desirable in the case of the car because now as you turn your accessories on and off, right, any accessories you have control over, it's going to maintain the voltage across the devices at 12 and everything's going to operate the way it should. Alright, well the next video is going to discuss why a regulator will only work within a specified range. As you can see here, we don't regulate voltage, or the range doesn't cover from the minimum of RL, which is 0, out to the maximum of infinity. So in the next couple of videos we'll look at, well, what happens if we're outside the range that's specified for a regulator? You know, what happens if we're below the minimum or above the maximum?